have a user. That user has a name, an email, 3 shipping addresses, and a dozen orders. Each order has multiple line items. Now ask yourself one question: where do you put all of that? A spreadsheet means duplicating the name and address on every single order row. A relational database means 5 tables, 30 join columns, and a query that touches 4 tables just to render one profile page. There is a third option. Store the whole user, everything about them, in a single self-contained document. That is what document databases like MongoDB are built for, and in the next few minutes you are going to understand exactly why that design decision matters. Before document databases existed, almost everything ran on relational databases. Spreadsheets and flat files could not handle complexity. SQL was the answer, and for a lot of problems it still is. But the relational model makes one fundamental assumption: your data fits neatly into tables of rows and columns, and every row in a table has exactly the same shape. The moment your real-world entities stop being flat, you start working against the grain of the model. A user is not a flat row. A user is a nested object with embedded collections inside it. You have to shred that object across 4 or 5 tables just to store it, and then reassemble it with joins every time you want to read it back. The relational model has 4 specific problems that compound as your application grows. First, the object-relational mismatch. Your application code works with objects and arrays, but your database stores rows and foreign keys. You need an ORM or a mapping layer to translate between the two worlds, and that translation is a constant source of complexity and bugs. Second, join queries multiply. A single page load might require joining users to addresses, orders to line items, and products to inventory. Each join is a cost. Third, schema migrations are painful. When your product changes and you need a new field, you write an alter table statement that locks millions of rows and requires a maintenance window. Fourth, normalization, taken too far, destroys read performance by scattering logically related data across many tables. Here is what a MongoDB document looks like for that same user: a single JSON object. The underscored field is a unique object TID generated by the database. Name and email sit at the top level. The addresses field is an array of embedded subdocuments, each with type, street, and city. The orders field is another array, and each order embeds its own items array inside it. The entire user with all their history and all their addresses lives in one place. To read a user profile, you issue one query. There are no joins. The document comes back as one unit because it was stored as one unit. This is the fundamental insight of the document model: keep together what you always read together. MongoDB is called schema flexible, but that phrase gets misunderstood. It does not mean no structure. It means the schema is enforced by your application rather than declared in the database up front. In a SQL database, you write create table, define every column and its type, and then every row must match that definition forever. In MongoDB, you insert any valid JSON document. Different documents in the same collection can have different fields. To add a new field to your user documents, you simply start inserting it. Old documents without that field still exist. Your red code handles both versions. This is called schema-on-read. When you do need hard guarantees, MongoDB supports optional JSON schema validation. You can require certain fields, enforce types, and reject documents that do not match. You get the flexibility by default and the rigidity when you need it. The most important design decision in MongoDB is whether to embed related data inside a document or reference it with an ID, the same way SQL foreign key works. The rule is simple: embed when you always need the data together and when one side exclusively owns the other. Order line items are a perfect example. You never fetch a line item without its order. The items array belongs to exactly one order. Embed it. Reference when data is shared across many documents or when either side has its own independent lifecycle. Blog post references its author by user ID rather than embedding the full user object, because the same user can author thousands of posts and you do not want to update every one of them when the user changes their name. The one anti-pattern to absolutely avoid is embedding arrays that can grow without bound, such as embedding every comment ever written on a popular post. MongoDB documents have a hard 16 megabyte size limit. Querying MongoDB uses a language called MQL, the MongoDB query language. Instead of SQL strings, you pass JavaScript-style JSON objects. To find all users in Sydney, you query on the nested field addresses.city. MongoDB traverses the array automatically. For more complex operations, you use the aggregation pipeline, a sequence of stages where each stage transforms the documents flowing through it. A group stage can sum order totals per user. A sort stage ranks the results. A limit stage returns only the top 5. The aggregation pipeline is more explicit than SQL and easier to reason about for data transformations. Indexes work on any field, including nested fields and array elements. Single field indexes, compound indexes, multi-key indexes for arrays, full-text indexes, geospatial indexes, and TTL indexes that automatically expire documents after a set duration. MongoDB is designed to scale horizontally. The first layer of scaling is a replica set, 3 or more copies of the same data running on separate machines. The primary node accepts all writes. Changes replicate automatically to the secondary nodes. If the primary goes down, the secondaries hold an election in seconds and one of them becomes the new primary. Your application reconnects and continues with no data loss. The second layer is sharding. When a single replica set is no longer enough, you distribute the data across multiple shards using a shard key. MongoDB hashes or ranges on that key and routes each document to the correct shard. A router process called Mongos sits in front of all the shards and makes the entire cluster look like a single database to your application. Choosing the right shard key is critical. A poorly chosen key creates hotspots where one shard receives most of the traffic while the others sit idle. MongoDB is the right tool when your data is document-shaped and your schema is likely to change. Content management systems, user profiles, product catalogs, real-time analytics pipelines, mobile backends, and IoT data streams are all natural fits. The schema flexibility means you can ship features without coordinating database migrations, and the document model means your query results map directly to the objects in your application code. MongoDB is the wrong tool when your data is genuinely relational, when you need complex multi-table joins as a core part of your query patterns, when you need strict foreign key integrity enforced at the database level, or when your team is deeply experienced in SQL and the schema has been stable for years. One last thing, MongoDB added multi-document ACID transactions in version 4.0. The old argument that you have to choose between MongoDB and transactions is no longer true. That is how MongoDB stores and retrieves data, documents not rows, embedding instead of joining, schema flexibility instead of upfront declarations, horizontal scale built in from the start. If this video helped you understand why the document model exists and when to reach for it, subscribe for more system design breakdowns every week. Thanks for watching.